In this video, we're going to go through the solutions to every question to the UKMT Senior Maths Challenge from 2020. That's the hardest of the main maths challenges in the UK, usually sat by students aged 16 to 18, often also taken by younger students as well. And if you're preparing for that challenge, do also take a look at my free course, Get Ready for the Senior Maths Challenge. In that course, you can practice all of these questions, as well as questions from other papers, and each one has a video hint and a full video solution. So you can have a go at the question, you can watch the hint if you're stuck, you can really have the best chance of getting the answer by yourself. You can see if it's right and then watch the video solution. It's a really great way to prepare for the Senior Maths Challenge. And over at that courses website, I've got loads more courses to prepare for maths challenges and for school maths as well. So I really hope you will take a look over there. But if you'd like to watch these solutions here on YouTube instead, I will get on with them now. I'll put timestamps below so you can jump to the questions you need if you are working through the paper like that, or if you want to work through the whole paper with me, we can start together here at question 1 and you can pause the video at the start of each solution. In question 1, we want to work out the value of 2020 divided by 20 times 20. They always try to get the current year in the paper somewhere in these challenges, and different ways you could approach this. I think my first instinct here is to think of this as 2020 divided by 20 and then divided by 20 again. So 2020 divided by 20 gives us 101, and then 101 divided by 20, well, that's 5 and 1/20th, or 5.05, and we can just get to the answer straight away like that. You could of course just do 2020 over 400 as well, and you could say that that's 5 and 24 hundredths, and that will also simplify down to 5 and 1/20th of course, which is also 5.05. So different ways of doing the arithmetic here and simplifying down the fraction. Any way you do it's fine. The first question is meant to be just a bit of a warm-up really. What's the remainder when 1, 2, 3, 4 times 5, 6, 7, 8 is divided by 5? The key to this question is that we can know the remainder when something's divided by 5 just from the last digit of the number, right? So, if the number ends in 1, 2, 3 or 4, then that will be the remainder, or if it's 0, then it's also a multiple of 5, and if it ends in 5, the remainder will be 0, if it ends in 6, the remainder will be 1, in 7, the remainder will be 2, etc. And the other key thing, something we've been using right from the Junior Maths Challenge courses here, if you have taken any of those, is this idea that when you multiply two numbers together, the product of the last digits is the last digit of the product. So actually here, all I need to do is look at the 4 and the 8 and say 4 times 8 is 32. The last digit of that number is 2. And so the remainder when we divide this product by 5 will be 2, because the last digit of the product will be 2. And then we're done. A shape is made from 5 unit cubes as shown. What's the surface area of the shape? Well, we can see if they're unit cubes, that just means they're 1 by 1. So the area of each individual square here is just going to be 1 unit squared. So what we need to do is just count up how many squares there are in the surface area, and you can see we've got on the top here 1, 2, 3, 4, 5, and there'll be another 5 of those on the bottom, and then we just need to count the ones that go around the side of the shape here, and you see we've got 4 cubes sticking out here. Each of them will have 1, 2, and there's a third one that we can't see here, so each of those will have 3. So if I add on 3 times 4, that will be 3 for each of those 4 cubes. 5 plus 5 plus 12 then is 22, and the answer is A, 22. We've got the numbers P, Q, R and S that satisfy these relationships. We can see P is 2, and then P times Q is 20. So if P is 2, we've got 2 times Q is 20, so Q must be 20 divided by 2, which is 10. And then we've got P times Q is 20 here, so we've got 20 times R is 202. That means that R is going to be 202 divided by 20 here, which is 101 over 10, which is 10.1. And then P times Q times R is 202, so I've got 202 times S is 2020, so S is 2020 over 202, which is 10. So P plus Q plus R plus S, that must be 2 plus 10 plus 10.1 plus another 10, that's 32.1, and so the answer here is B. So the idea here isn't to actually work out the square root of this number directly, we've got 5 options here, and we should be able to come up with a reasonable sort of guess as to which one is right here. Well, more than a guess, we'll deduce exactly which of these it is by just thinking about how many digits there are going to be. So, if I took E, if I just did like 100 squared, that would be 100 with 2 more zeros, that would be 10,000. So that's obviously clearly far too small here. Now 111 squared would obviously be a bit bigger than this, but it's not going to be way bigger. It's probably, it's going to give us something with this sort of pattern, but it's going to be that sort of size. So similarly, if I've got 1,000 here, that would give me something like 1 million. Now this number here has 1, 2, 3, 4, 5, 6, 7, 8, 9 digits. So actually when you think about doing 10,000 squared, well, that's going to have 4 zeros and then another 4 zeros. So that's going to have 9 digits. And we're meant to deduce from that that the answer must be C. So I've got a 9-digit number here. It's going to be a bit bigger than the square of 10,000, roughly the right sort of amount bigger. If I go to this one, it's way bigger. It's going to have 2 extra digits. If I use this one, it's going to be far too small. So if the answer is any of these, it must be C. We don't have to actually check the full multiplication out to be sure of that, given we've got the answers. We want to save time in the maths challenge, deduce that the answer is C, and then move on as quickly as possible. In question 6, it says there are fewer than 30 students in an A-level maths class. Half of them play the piano, a quarter play hockey, and a seventh are in the school play. So the key here is to know that the number of students must be an integer, must be a whole number, and that means that if I can have a seventh of them, the number must be a multiple of 7. If I can have a half of them playing the piano, then it must be a multiple of 2, and if a quarter of them play hockey, there must be a multiple of 4. So we need it to be a multiple of 2, a multiple of 4, and a multiple of 7. Obviously, anything that's a multiple of 4 is automatically a multiple of 2, so we don't have to worry about that. 4 and 7 don't have any factors in common, so the lowest common multiple of 4 and 7 is 4 times 7, which is 28, and in particular, that's the only multiple of 4 and 7 that's smaller than 30. There must be 28 students in the class, and it says how many play hockey. Well, it's a quarter that play hockey, so we've got 28 divided by 4 is 7, and the answer is E7. Official UK accident statistics showed that there were 225 accidents involving teapots in 1 year. However, in the following year, there were 47 such accidents. What's the approximate percentage reduction in recorded accidents involving teapots from the first year to the second? So really what we want to know here is, what is 47 as a fraction of 225, as a percentage of 225? So there's a couple of ways we could do this. We could just kind of round 47 to a close-ish whole number, or we could say, well, if I look at 225, I know 10% of 225 is 22.5, so 20% would be 45, and so actually this number is going to be closest to 20%. It's going to be closer to 20% than 30% surely, which is going to be 67.5. So it's a 20%. So it's 20% of the year before. That means an 80% reduction, and so the answer is D. You could also do this by rounding 47 down to 45 first, or up to 50. Again, you could do 50 over 225 is 2/9 or something, which is so that's 22.2 recurring percent, and then you could say, it's a bit too much, so we've rounded up. So if I go back down to 47, it'll be 20% will be the closest again. So however you get there, the answer is D, 80%. Got a classic maths challenge question here. What's the largest prime factor of 106 squared minus 15 squared? Of course, we're meant to rely on the difference of two squares formula here that says that x squared minus y squared is x plus y times x minus y, giving us a nice factorization of the result here. So if I take 106 squared minus 15 squared, that's the same as 106 plus 15 times 106 minus 15. That gives me 121 multiplied by 91. 121, of course, is 11 squared, 11 times 11, and 91 is 7 times 13. So the prime factors of the answer here are 7, 11, and 13, and the largest one of those is 13, and so the answer is D. Question 9, we've got a racing driver being allowed to use the drag reduction system provided the car is within 1 second of the car ahead. And it says, suppose there are two cars that are 1 second apart, and they're each travelling in the same direction at 180 kilometers per hour. How many meters apart are they? Well, really this question then is just asking you, in 1 second, how far would these cars travel, right? That's the distance they are apart here. They're both going at the same speed. They stay the same distance apart. So it's just saying how far would this travel in 1 second to get here. So 1 hour, that's 60 minutes, or 60 times 60, which is 3,600 seconds. So if we're going 180 kilometers every hour, in each second we'll go 180 divided by 3,600 kilometers, which is, we can divide top and bottom by 10 here. We've got 18 over 360, which is 1/20th, so it's 1/20th of a kilometre. You can times that by 1,000 to make that into meters, and that gives us 50 meters, which is 1/20th of a kilometre, and so the answer here is B. Right, we've got a bit of a logic question here. We've got these 6 friends, Pat, Kazim, Raymond, Sam, Tara and Uma, standing in line for a photograph. I'll just call them P, Q, R, S, T and U from now on. There are 3 people standing between P and Q, so let's just draw that. So I've got P and Q, and then let's just say there are 3 gaps. 2 people between Q and R, so R could certainly be here. Could R be the other side? Well, if there was 2 people between them on the other side, there would now be 8 people at least in this line. There's only 6, so it must be actually that R is over on this side. And then it says there's 1 person between R and S, and Sam is not at either end of the line, or S is not at either end of the line. So if there's 1 person between R and S, well, S could be here, or S could be here. But if S was here, then S would be at the end of the line, because that would be 6 people in total now. So it must actually be that S is here. Now it says how many people are standing between T and U. We don't know where they are, but this one must be either T or U, and then the other one of T or U must be either to the left of P or to the right of Q here. So it could be here or could be here, but either way there'll be 2 people between them, either these 2 or these 2, P and R, S and Q. So whichever arrangement they're in here, it must be that there are 2 people between Tara and Uma, and so the answer is C2. In question 11, we've got 2 congruent pentagons, each formed by removing a right-angled isosceles triangle from a square of side length 1. We fit them together and we end up with an octagon, and so we want to work out its perimeter. Now, some parts of the perimeter are easier than others. Obviously, I've got this one, these side lengths are 1, 1, 1 and 1. So the 2 things I need to work out are what's this length here and then this length here, or also now. So you could actually work those out directly, or you could just look at these 2 together and say, oh well, look, this plus this is just the same as this plus this, so those 2 together actually form 1 unit. And similarly, if I look at this bit and this bit here, well, again, this one is the same as this length here, so that's also 1 full unit. So in total we've just got 6, and the answer here is 6. Just for completeness, if you did want to work out those 2 parts individually, you could do, all you'd have to do is note you've got this right-angled isosceles triangle here, and that length is 1. So if I call these side lengths x, by Pythagoras theorem we'd have 2x squared is equal to 1. X squared plus x squared is 1 squared, so x would be 1 over the square root of 2. So this side length here would be 1 minus 1 over root 2, because it's 1 minus that bit, and this one would be 1 over root 2. And again, when you add those together, you get 1, and if you do that twice, also with this one and this one, again, they add together to get 1. So you could work all the side lengths individually here, but there's no need to. The first argument is nice and neat, saves us a bit of time, and lets us get on with the paper quickly. And the answer then is E6. A 3-piece suit consists of a jacket, a pair of trousers and a waistcoat. We've got 2 jackets and 3 pairs of trousers, cost £380, so let's write that as 2J plus 3T is equal to 380. We've also got that a pair of trousers costs the same as 2 waistcoats, so we know that T is equal to 2 times W, where J, T and W are obviously the price of each item individually. And it says, what's the cost of a 3-piece suit? Now, more information needed is very rarely the right answer in a maths challenge question. I'd forgive you for thinking it might be the right answer here, because I've got 2 pieces of information and 3 unknowns, and usually you need 3 pieces of information for 3 unknowns, but we don't actually want to work out J, T and W here all individually, it's enough just to work out what J plus T plus W here is. And with these two pieces of information, we can actually work this out without working out what the values are individually. And the little trick here is that, well, if you look at this first equation, 2j plus 3t, I could write that as 2j plus 2t plus another t, that would be 380, but then the t is 2w, so I've got 2j plus 2t plus 2w, that's 380, and now if I divide this whole thing by 2, I get j plus t plus w is 380 divided by 2, which is 190, and so we can see that the answer to the question is B, £190. So the number 16 factorial divided by 2 to the k is an odd integer. It reminds us here what factorial is in case we haven't seen it before. So 16 factorial, I'm actually going to write out in full here because it's going to be useful. So it's 1 times 2 times 3 times 4, etc. All the way up to 16. Now, so if I'm going to divide this by 2 to a power and I'm going to end up with an odd number, all of the factors of 2 have to have disappeared. So like if I divided this number by 2, I would just get the same thing but without the 2 here. If I divide it by another 4, which is 2 squared, I would get rid of that 4, and what's left are just odd numbers here, and I multiply odd numbers together, I'll get an odd number. In the 6, there's also going to be a factor of 2, so if I divide by 2, that would give me this number. If I divide by the 8 here, which is 2 cubed, that will cancel out. For the 10, that's got a factor of 2, that would leave a 5 in here. For the 12, that's got a factor of 4, sorry, not 2 to the 4, 4 which is 2 squared, and that would leave me with a 3, and the 14 has a factor of 2, which would leave a 7, and then if I divide by 16, which is 2 to the power of 4, then everything that I've got left here will be an odd number. Now if I divide by any more 2s, I'm dividing an odd number by 2 and it won't be an integer anymore. So this is exactly the number of 2s that I need to divide by to get an odd integer. So how many are there in total? 1 here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and the answer here is D, 15. So in question 14, Diane's got 5 identical blue discs, 2 identical red discs, and 1 yellow disc. And she's going to place them in this grid, and I've just made a bigger copy of this down here, so that there's one of these discs in each cell. The 2 red discs can't be placed so that they have in cells that have a common edge. So now I think the key to this question, I mean there are other ways of doing it as well, but I think because there's this sort of restriction on the red discs, it makes sense to start by thinking about where the red discs go, I think. At least that's how I thought about it. So let's say I put a red disc here. How many other places could I put this other red disc? Well, I can't put it here or here, but I could put it here, 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 or here. So there would be 5 possible ways of having a red disc in this corner. Now, what I do next is I think, okay, well, what if the red disc the first red disc was here? How many places are there that I can put this next one? Well, again, I'm not going to consider, well, now obviously I can't actually put it here because they'll be next to each other, but as I go through, I'm not going to consider any that involve this square or any others that I've already considered, right? So you'll see what I mean in a second. So with this one, I could put it either here, 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 or here, but not in the ones here or here. So there's 4 that would have a red disc there. Now, so like when I consider this next one, right, I'm going to count them, but I'm obviously not going to count this one because I've already counted it as part of that 5. So where else could I put it? Well, 1, 2 or 3 positions left for that one, and then if I put it here, there would also be 3, 1, 2 or 3 here and here, here and here, sorry. And now if I put it here, again, I'm not considering any of the ones that I've already done before. It can't go here, but it could go here or here, so there would be 2. And if I put it here, there's only 1 left here because I can't put it next to it. And then there's no way that uses these 2 without using one of the other ones because I'd have to put them here and here, but they'd be next to each other, so there's no more. So there'd be 5, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 ways of positioning the red discs. Now just think what happens when you've got the 2 red discs somewhere, right? Let's say they're here and here. And what I've got left to do is to put in 5 blue discs and one yellow disc. Okay, so you know I might put in blue, 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 and then we'll put a yellow one in the last spot here. Because there's only one yellow disc, well, how many ways are there to do this? Well, I could just put the yellow one in any of these 6 remaining spaces, and then the blues will just fill up the rest. So for any particular combination, there's 6 ways of putting the yellows in the blues. So I'd need to do 18 times 6, that's 60 plus 48, which is 108, and in total, then there are 108 different looking completed grids that it's possible to produce. So we've got this picture and it says the shaded area in the diagram is the interior of a circle of radius 3 with this area between the circle and the 2 tangents to the circle. And the angle here is 60 degrees, and we want to work out the total shaded area. So the thing we should know about tangents is that they meet the radius to the circle at right angles here, and that's going to be a really key to this question. I might not draw it perfectly accurately here, but it'll be close enough for a diagram. And if I also draw, I think, a line down the middle here, that makes sense. So I've got these 2 congruent triangles, and so rather than actually taking the circle and then trying to add on this part here, actually what we'll do is we'll take a sector of the circle here, right? If this is 60, then each of these is 30, so these are also 60, so it's 120 here, so this side is 240, right? So this bit is going to be 2/3 of the circle, 2/3 times pi r squared, which is 2/3 times 9 pi here, which is 6 pi, and then we'll add on these 2 triangles. So they're right angle triangles, so I can just do half base times height for them. The base is the radius of the circle, which is 3, and you could work out the height here using SOHCAHTOA if you wanted to, if you know sine, cos and tan or whatever. Actually it can be quite useful to know sine, cos and tan of 30, 60 and 45 for the senior maths challenge. Even for the intermediate maths challenge you can make use of it, but I don't like to use those if I don't have to. So another way of doing this would be to just paste these 2 triangles together here and say, okay, what I want is the area of this triangle. That would be the same as these 2 bits put together, this whole equilateral triangle here. And it is an equilateral triangle, right? Because it's 60 at the bottom here, it would be 60 at the top here, and so it would be 60 here as well. So if it's an equilateral triangle, and we can see that the base here is 3, and this is exactly half of the base, that length would be 6, and so this length up here would be 6 as well. And so actually looking at this triangle in here, right, we can say, I've got a right angled triangle here, and the length here is 3 and this is 6. So if this is x, I've got 3 squared plus x squared is 6 squared, so x squared is 36 minus 9, which is 27, so x is the square root of 27. We should be good enough at surds for the senior maths challenge to write this as the square root of 9 times the square root of 3, which is 3 root 3. So I've got that this height here then is 3 root 3. This base along here is 3, or the whole thing is 6. So the area of this triangle is a half times the base of 6 times the height of 3 root 3. That's doing the 2 triangles together. So that's 9 root 3. So to get the total area, I'm just going to add this 9 root 3 to 6 pi, and we get 6 pi plus 9 root 3, and the answer is A. The argument I've made here about the equilateral triangle, by the way, is exactly how you would prove what the values of sine, cos and tan of 30 and 60 degrees are. Start with an equilateral triangle, say you know what the side lengths are, and then deduce what sine, cos and tan of 60 degrees are, and 30 degrees are. So actually, in a lot of the maths challenge questions where it looks like you're meant to use like just remembering those things, you can often find ways of doing it more directly like this. But of course, it can be handy to have all the tools at your disposal, so just memorizing those values, just as I say, just for 30, 60 and 45, I think could be quite useful if you want to, or at least remembering how you prove them from an equilateral triangle, and the other one you prove for 45 from a right angle isosceles triangle like this. And from that triangle you can deduce sine, cos and tan of 45 degrees. So we want to know which of these diagrams represents the set of all the points satisfying y squared minus 2y equals x squared plus 2x. We might call that the locus of the points, sometimes the graph, although we need to be a bit careful about the technically what those things mean. But really what we've got is a diagram where on each of the diagrams, if the coordinates of a point satisfy the algebraic relation, then that's a point on the diagram, and if it's not, it's not. So one way when you've got a multiple choice question like this, to work out which one is which, this happens a lot on the Oxford Maths Admissions Test questions as well actually, is that you can sort of find some points and that must lie on the diagram here and then rule out some of the options. So perhaps the most obvious thing to do here is just to factorize each side of this equation and say y minus 2 is equal to x times x plus 2, and now I can see I can get 0 equals 0 here by either making x equals 0 and y equals 0. So 0, 0 must lie on here, and in fact 0, 0, the origin is on all of these, so that doesn't help us too much. But we can also see that 0, 2 would make x is 0, y is 2 would make both sides 0 here. I could do x is minus 2 and y is 2, and I could also then do y is 0 and x is minus 2. So if I think about the ones where I've got axis intersections here, I must have a y-axis intercept that's above 0, so that could be A or B, but it can't be C, right? There's no 0, 2 isn't on that one, and similarly it can't be D, 0, 2 isn't on that one, and it could be E. If I look at minus 2, 0, well, okay, that point is not on A, clearly it just goes to the origin here. It could be this point could be minus 2, I don't know it, but it could be, and this point could be minus 2. So I've narrowed it down to B or E, so I've got a 50-50 guess, and now I've got to look at these two diagrams. Now I've got either these curved with some values of y that are just not attainable, and actually one way to do this would be to look through this and say, oh, okay, if I take some values of y, you might start thinking, okay, is it possible for there to be any values of y where there isn't a value of x? You could go down that line of thinking that's not what I'm going to do here, because actually what I've also got in the second one is two straight lines, and in particular this second straight line, the one that goes down here, looks pretty identifiable to me. It looks like it's probably y equals minus x. Now again, we haven't got the scales on the axis, so we don't know that for sure, but once you've had that thought, you can look at this and say, oh well, hang on, what happens if I just put y equals minus x, right? I get minus x squared minus 2 times minus x on the left hand side, and that simplifies to give x squared plus 2x. So actually any point where y is equal to minus x, any pair of coordinates where I've got 2 minus 2 or 4 minus 4 or minus 6 6, they must all lie on the diagram. So actually that line y equals minus x must be totally included, and so it's not there in B, so we've narrowed it down to E. In fact, this other line you can also work out. Well, we know it goes through 2 and minus 2 here, so actually it must be the straight line y is equal to x plus 2, and if you substitute y equals x plus 2 into the left hand side and get x plus 2 squared minus 2 times x plus 2, then you get x squared plus 4x plus 4 minus 2x minus 4. The 4's cancel out and I get x squared plus 2x as well. So again, any pair of coordinates that satisfy y equals x plus 2 must be in this diagram, and so really the answer here is E. So I think that's the sort of way I would kind of practically go about these questions. First, look for some points that can really narrow it down. Sometimes that might just get you to the answer, and then we might have to do something a bit more clever. Kind of once we've got that answer, we might see an even better way of doing it, or perhaps you might even have started by this method. We could rearrange this original equation to say y squared minus x squared equals 2x plus 2y, and then we could factorize using the difference of two squares here. Y minus x times y plus x is equal to 2 times x plus y. So actually if I think of this side as y minus x times x plus y is 2 lots of x plus y, and then let's subtract the 2x plus y from both sides. Then we get something like this, and now I've got y minus x lots of x plus y minus 2 lots of x plus y, so I can do another factorization here and say, well, that's just y minus x minus 2 lots of x plus y equals 0. And then we get to the either from this second bracket y is equal to minus x, or from this other bracket we get y minus x minus 2 is 0, or y is equal to x plus 2, and that's another way of seeing that the answer must be E. I don't think this question is quite as hard as it looks. We want positive integers m, n and p that satisfy this equation. A little bit of trial and error should really just get us there very quickly. Certainly if we look at this, what have we got at the structure? We've got 3 times m. Well, if m is an integer, that's certainly going to be an integer, so if I do 17 minus that, I need to get an integer. So the key problem here is to make this thing an integer, and then we'll check that it makes the whole equation work as well. So if I'm going to do 3 divided by n plus 1 over p, these have both got to be integers, positive integers, right? And this overall thing has to be an integer. So, like, if I make n 2, 3 over 2 plus something is not going to be an integer. It's not going to be a whole number. So actually, and if I make it any bigger, 3 over 3 plus something, 4 plus something, 5 plus something, I mean, there's no other way of making this an integer apart from taking n equals 1 here, and then I just have to think of what fraction will make this an integer. Well, it's going to have to be 1/2. I don't know if that's obvious. If you think about different values, you don't have to try too many to work out this. You try 1, it doesn't work, 2, it does work, and then as soon as we've got that, we've got 3 over 1.5 here, which is 2. So I just check that there is a value of m that makes this work. So I would have 3m plus 2 is 17, so 3m is 15, and then m equals 5. So I've found 3 values that work here. And in the maths challenge as well, if you've got values that work, you don't have to think too much about whether they're unique, because this question has been posed as it has. They must be unique. So we must have n equals 1 here, p equals 2, and m equals 5, and so the answer is A2. Two circles C1 and C2 have their centres at the point 3, 4 and touch a third circle C3. The centre of C3 is at the point 0, 0 and its radius is 2, and we want to work out the sum of the radii of these two circles, C1 and C2. I'm not going to worry too much about that at the moment. I think I'll just look at the information and start trying to draw a picture. So let's try and draw C1 and C2 to begin with. Now, I'm going to use the circle tool here. Obviously, if you can draw reasonably good circles freehand in the actual maths challenge, that's quite useful. So we'll have concentric circles here. I'll just do it roughly. I'm not going to get it right here, I think. Anyway, so they're at 3, 4, and I need to now make this third circle C3. Okay, so let's just call these ones C1 and C2. C3 has to just touch these two circles and have centre 0, 0. Now, there's kind of two ways that I could make another circle just touch these two, right? I could maybe have, one something like this, but you quickly realize that in this situation, okay, I can't quite get it to exactly touch here, something like that. In this situation, okay, if the center of this one is the origin, right, well, this distance from the origin to 3, 4, it'll be a 3, 4, 5 triangle. So actually this circle's would end up having a radius much bigger than 2. Okay, so the other way we can do it is to put this third circle somewhere down here, and so it's sort of like just in between these two circles, and this looks a lot more reasonable that it could have a radius of 2. Okay, so if this is the origin, let's just make that argument a bit more clearly about this 3, 4, 5 triangle. Okay, so that means that this length would be 3, this would be 4 by Pythagoras. We've got 3 squared plus 4 squared is 5 squared, and this length is 5. So that means that we know that this radius is 2, and then this one, the radius of the circle here must be 3, and then this distance is also 2. And if you put those three things together, you get the radius of C2. So C2 has its radius, let's call it R2, is equal to 3 plus 2 plus 2, which is 7, and C1 has radius R1 here, which is 3. So the sum of the radii here of C1 and C2 would be 7 plus 3, which is 10, and the answer is E. So I don't think there's any need to overthink this one. There's only, 9 or 10, I suppose, single digit numbers if we include 0, to check here. We want to make P minus Q equal to R, and R minus S to be equal to T, and how many different values could T take? So let's just run through them. Okay, so if T is 0, R and S would have to be equal, so we can't make T 0. If T is 1, I can just start trying to find things that work. So 3 minus 2 is 1, and then R would be 3, So I could do something like 9 minus 6, nice and easy. So let's write the ones that have worked up here. So 1 works. For 2, I could now try and do 3 minus 1 is 2. Actually, this is the same as I've just done before in the last one. I could also have 9 minus 6 is 3 here, so 2 works. For 3, I could do something like 4 minus 1. I'm trying to just choose these as small as possible to give myself plenty of choice for the other equation here. So 4 could be something like 9 minus 5 without repeating anything. So that gives me 3 as a possibility. Here, if I want to make it 4, I could do 5 minus 1 and make r equal to 5. Now, I can't do 9 minus 4 here, but I could do, say, 8 minus 3 and get 5, and they're all different, so we can certainly do 4. If I want to do 5, again, let's do 6 minus 1, and then I need to make r equals 6, so I could do something like 8 minus 2 to make them all different, and so t equals 5 works. And when I try t equals 6, let's do 7 minus 1, I'd need to make r equal to 7, and then I could do something like 9 minus 2 to make them all different, and so 6 works as well. I can actually stop now because we found 6 values that work, and that's the largest possible answer here, so the answer must be A, 6. If you do try other ones, if you tried to go to 7 here, now I'm going to have to do something like 8 minus 1, but then to get 8 I'd have to do 9 minus 1, which I can't do, and I can't do 8 minus 0 without repeating. I could also do 9 minus 2, but then I'd have to make the difference 9, and that also doesn't work. And the same if you try 8 here, I'm going to have to do something like 9 minus 1, but then I can't make the difference here 9. So you can't do any other values, but as I say, you don't really need to check those last ones. Once you've found 6 that work, you know that the answer is A, 6. So this question is really about being good at indices. If you want some video lessons about indices, check out my course, Get Ready for A-Level Maths. The videos about indices are actually part of the free part of that course, so you could watch those and get really good at this topic before you do this question. I'm going to assume you know the rules of indices here and just go ahead and solve it. So the first equation we've got here, 4 to the y is 1 over 8 times root 2 to the x plus 2. You could write 4 as 2 squared, and so that would be 2 squared to the power of y, and then 8 would be 2 cubed. Now root 2 is 2 to the 1/2. Again, that's something you should, I'm just going to assume that you know as a fact, but look it up if not, or look at that Get Ready for A-Level Maths course. And that's to the power of x plus 2. Now when I've got 1 over an index, that makes the index negative, and okay, maybe I should simplify the denominator first here actually. So this would be 2 to the, this bit here would be 2 to the half x plus 2, and then I've got 2 to the 3 times that, so it would be 2 to the 3 plus 1/2 x plus 2, but it's 1 over that, so actually it's 2 to the minus that, so 2 to the minus 3 plus 1/2 x plus 2, and on the left here I'd have 2 to the 2y. So okay, I've got both of these as 2 to the power of something, so I can just say 2y is equal to minus, let's write this as minus 3 minus 1/2 x plus 2, and I'll tidy it up a bit by multiplying by 2 both sides. 4y is equal to minus 6, and then minus x minus 2, or 4y is equal to minus x minus 8. Okay, now the other one's a bit easier to deal with. 9 to the x, that's 3 squared to the x, so that's 3 to the 2x, times 3 to the y, and 3 root 3, that's 3 to the 1 times 3 to the 1/2, so that's 3 to the 1.5. And so I've got 2x plus y is equal to 1.5. So I've got, let's write 4x plus 2y is equal to 3. So I've got rid of, well, I've got everything in nice whole numbers. So I've got two simultaneous equations here for x and y. If we, let's take the second one and double it, and then we've got 8x plus 4y is equal to 6. So 4y is equal to 6 minus 8x. If I substitute that in here, I get 6 minus 8x equals minus 8 minus x. But you can solve the simultaneous equations however you want here. I'm assuming, again, that's something you know how to do. So if I add the 8x to both sides, I get 7x, and add the 8 to both sides, I get 14. So I get x equals 2. And if we just plug that back into one of these equations, let's put it into this one here. I've got 4y is equal to minus 2 minus 8, which is minus 10. So y is minus 2.5. And then that means that x plus y is 2 minus 2.5. That's minus 0.5. So finally 5 to the x plus y, that's 5 to the minus 0.5, that's 1 over 5 to the 0.5, which is 1 over the square root of 5, and so the answer is E. As I say, I've done that a bit quickly because I'm sort of assuming that you know how indices work here. The main thing for this question is just to have learnt about indices, watch those other videos in the course Get Ready for A-Level Maths if you want to, and be pretty slick at them. Actually, once you know about indices here, it's fairly clear what you have to do in this question. I think if you've seen a question like this before, there's just a bit of work that you've got to go through and solve the simultaneous equations and get the answer. Right, this is quite a nice question. Pay attention to the form questions are given to you in. There's often a clue in the way things are written down. Here it says we've got 10 to the 2020 plus 2020 all squared. Again, the maths challenge getting the current year 2020 in a lot in this paper. But this should really remind you of just the form x plus y squared, and we know that x plus y squared is x squared plus y squared plus 2xy. So I think my first thought here is to write this as 10 to the 2020 plus 2020 squared, so take x equals 10 to the 2020 and y equals 2020, and then I'm going to get 10 to the 2020 squared, which by the rules of indices is just 10 to the 4040, and then I've got to do 2020 squared and then 2 times 10 to the 2020 times 2020. Okay, so actually each of these things are reasonably easy to deal with, right? 10 to the 4040 is just going to be a 1 with a lot of zeros after it, right? 4040 zeros, I guess. And this gives us this 4041 digit number overall. 2020 squared, well, we can just work that out. I suppose I could do, let's do 202 squared, I suppose. So 200 times 202 would give me 40400, and then I'd need to add on another 2 lots of 202, so that would be another 404, so I'd get 40804, or you could just do it as an ordinary multiplication if you want to, and of course that was 202 squared, so 2020 squared would have another 2 zeros on the end, and then 2 times 10 to the 2020 times 2020 would be 4040, and then loads of zeros on the end, like 2000 zeros, 2020 zeros, right? So now the final answer we've got here is just these things, added together, these three numbers added together. But this one's got like over 4,000 zeros in it, so I'm going to start with the 1, and then after like a couple of thousand zeros, finally, this number will appear here, so I'll get 4040, whatever, and then this number here won't appear until the end, so I'll add that on and I'll get 4080400. So I can actually write down this whole number quite easily, as long as I don't actually want to write out all the zeros. Because those bits don't overlap, I can say, well, what's the sum of the digits? Well, just add these together. I get 1 plus 4 plus 4 plus 4 plus 8 plus 4. That's 12, 16, 24, 25. And then the answer is C, 25. So we've got a square with perimeter 4 centimeters. That means that the side length of the square is going to be 1. And it can be cut into 2 congruent right angle triangles and 2 congruent trapezia as shown in this diagram. So the 4 pieces can be rearranged to make this rectangle. And we want to know what the perimeter is in centimeters of this rectangle. So we've got to work out what the lengths are in this picture, I think. Now, the key thing that matches up here is this side here, right? So that means that the shorter side of the triangle here and the shorter side of the trapezium are going to be the same length. So let's just call that x, and then that x as well. They must be equal, and then from that we can work out all of the other lengths, right? This is 1 minus x, so that means that this is x and 1 minus x as well. This bit here must be 1 minus x and 1 minus x and x, so I've got every part of that labelled. So I can also go through the rectangle and do the same thing. Well, this must be 1 minus x, this must be 1 minus x, this is 1, this is 1 minus x, this is 1, and this is 1 minus x. So the perimeter in terms of x is just going to be all of these added together. So I've got 4 lots of 1 minus x and then 2 1s. So that gives me 6 minus 4x. So if I can work out what x is, we can certainly work out the perimeter. So there's a couple of ways you can do it. I think matching up the areas of these two shapes is one way that makes sense. I think when I looked at this, I thought about similar triangles. So so let me just say, you could just do this by saying area of square equals area of rectangle, and that will give you an equation. But I looked at this triangle. I think so I've thought about similar triangles too much probably in my life, but what you've got here is 1 and 1 minus x and 1 minus x here, and then this would be x. So by similar triangles I could say that x over 1 here is equal to 1 minus x over 2 minus x, right, because this length is 2 minus x. So I'm saying I've got two similar triangles, the small one here which has got sides x and 1, and the equivalent sides on the similar larger triangle are 1 minus x and 2 minus x, like that. So we can just turn this into an equation. Well, it is an equation. We can multiply by 2 minus x and get 2x minus x squared equals 1 minus x. So I've got 0 equals x squared minus 3x plus 1 here, and we can certainly solve this however you want to find x. Let's just use the formula. X equals 3 plus or minus the square root of 9 minus 4 divided by 2. So that's 3 plus or minus the square root of 5 over 2. Now, if you think about it here, 3 plus root 5 over 2 is going to be way too big to be sensible in this question. So actually we're going to just take 3 minus root 5 over 2 to be x. And then we've just got that the perimeter that we're looking for is 6 minus 4x. So that's 6 minus 4 lots of 3 minus root 5 over 2. And this works out quite nicely because 4 times 3 over 2 is 6. And I've got minus root 5 over 2, so that's plus 2 root 5. The 6's cancel, and we get the final answer that the perimeter is 2 root 5. A function f satisfies y cubed times f of x is equal to x cubed times f of y, and we know that f of 3 is not equal to 0. And so we want to work out what the value of f of 20 minus f of 2 divided by f of 3 here is. Obviously, if f of 3 was 0, this wouldn't really make sense. So it might be a bit hard to work out where to start here, but really I think the only numbers we've got here that could be sensible for x and y that would be useful will be 22 and 3. So we might just start playing around with those. So if you substitute in different combinations, you'll find that the thing that's useful here is to, if you make one of them 3, so let's say make f of y, so let's make this f of y f of 3, so let's make y equals 3, and then let's make x equals 2, right? So x equals 2 and y is 3. Putting that in here gives me y cubed, which is 27, times f of 2 is equal to 2 cubed, which is 8, times f of 3. And the nice thing about this, you see, is that it allows me to write f of 2 is equal to 8 27ths times f of 3. And now when you think about this, this is going to be helpful. Because if I also do x equals 20 and y equals 3, that would tell me that 27 times f of 20 is 20 cubed, which is 8,000 times f of 3. And that would give me that f of 20 is equal to 8,000 over 27 times f of 3. So when I'm looking at this f of 20 minus f of 2 over f of 3, what I've got is 8,000 over 27 times f of 3 minus 8 27ths times f of 3 divided by f of 3. So we can factorize an f of 3 in the top if you like here and say, well, this is just f of 3 times 8,000 over 27 minus 8 over 27 divided by f of 3, or you can just cancel it right away if you can see that, and they cancel out. So I've got 8,000 27ths minus 8 27ths, so 8,000 minus 8 is 7,992 divided by 27. So we could do the division by 27 directly here if you want to, or we could do something like dividing it by 3 times, or dividing it by 9 and then by 3. Let's divide it by 9 and then by 3. I think that's going to be reasonably quick. So 9 times 8 is 72. We've got 7 left over. 9 times 8 is 72 again with 7 left over, and then 9 times 8 is 72. So I've got 888, and then I just need to divide that by 3. So I've got 2 with 2 left over, and then I've got 9 with 1 left over, and that gives me 296. And so the answer must be D, 296. So for this question, I've just made a bigger copy of the diagram here, and we will just go through the question and annotate it slightly. So in the diagram, M is the midpoint of PQ, okay? The line PS bisects RPQ, so the angle RPQ. So actually I'm just going to label this one X, and then this one will be X as well, and that's bisecting it. So the line ST is parallel to PR, so this one and this one are parallel, and intersects PQ at T, okay? The length PQ is 12, so that's that whole length across here, and the length of MT is 1, okay? So the angle SQT is 120 as shown. What's the length of the angle? What's the length of SQ? That's what we want to work out here, this part here. Okay, so you need to look at this quite carefully. You probably have to look at it for a while. And really with this question, just write in anything you can. Something that occurs to me fairly early on in this question is that we have to use the parallel lines somehow. And when I've got parallel lines, sometimes it can help just to extend them to sort of see the cases of the theorem. I think the official solutions here go a little bit around the houses to work this out, this first step, but actually this angle here is just alternate to this angle here. So we've got alternate angles, this one is equal to X as well, and that means that this triangle PTS is isosceles. Now we've got the information about the lengths here, so P to M would be 6 and M to T is 1, so that length is 7, and that means that because this is an isosceles triangle, PTS, that this length here would be 7 as well. And of course we know that the length TQ would be 5, because the total here is 12. Now if we just look at this triangle here, let's just draw it again so it's a little clearer. We've got STQ, so that length is 7, this is 120, and this is 5, and we want to work out y here as the answer to the question. So we're just going to apply the cosine rule to this. So let's just get that out of the way a little bit. And so the cosine rule say a squared equals b squared plus c squared minus 2bc cos a. And I'm going to have to take this as the angle A then. This is A, and then either of these is B and C. So I've got a squared is 49. That's going to be y squared plus 25 minus 2 times 5y, so that's minus 10y times cos of 120. Now for the Senior Maths challenge, we should be able to work out things like cos of 120. This is a topic that I cover in the course Get Ready for A-Level Maths. The teaching videos in that course are available for free, and so there's some videos talking about working these things out in there, so I'm going to assume that you kind of have seen this sort of thing before. There are different ways of doing this, but I'll do it with just a quick sketch of the cosine graph. This would be like y equals cos x or something, so it goes through 90 here. So if this is 60 and 120, they're kind of symmetrically opposite each other. So all I'm trying to work out in my head here is just to remember that I know that cos of 120 is minus cos of 60, and cos of 60 hopefully you know is a half, and if you don't, you could also work that out quickly by doing something like drawing an equilateral triangle. Sometimes in maths it's just as good to remember how to derive things as it is to actually memorize tons of things. So if you take an equilateral triangle with side length 2, then the angle here would be 60, and we can see from this right angle triangle that cos of 60 is the adjacent over the hypotenuse, which is a half. So anyway, I got cos of 120 is minus a half, so this becomes 49 equals y squared plus 25, and then I've got plus 5y when I replace that with minus 1/2. So we've got y squared plus 5y minus 24 is equal to 0 then. We can factorize that as y plus 8 times y minus 3 is 0. So this length we're looking for is either minus 8 or 3. The length can't be negative, so it must be the case that the length SQ that we're looking for is 3, and the answer is B. So question 25 is always going to be a tough one. This is no exception. And we've got a regular m-gon, a regular n-gon, and a regular p-gon. They share a vertex, and pairwise they share edges, as is shown in the diagram here. I want to know what's the biggest possible value of p here, i.e. what's the largest number of sides that one of these polygons could have. Now, one thing I always think is it's easier to work with exterior angles than interior angles, just because the formula is simpler, and so something that occurred to me here is that if we just extend this line out here, I've just written this diagram without the words on it, then this would be the exterior angle for the m-gon, right? Just those two would add together to give 180. This would be the exterior angle for the n-gon, and this would be the exterior angle for the p-gon, and we can see that the exterior angles have to add up to 180 degrees. We get a straight line there. Okay, so that's what I'm going to use here to solve this problem. So the exterior angles are just 360 over m, and we're going to have 360 over n and 360 over p. They have to add together to give 180. And if we divide this all by 360, we just get that 1 over m plus 1 over n plus 1 over p is equal to 1/2. So we've reduced the problem to just solving this equation for I need whole number integer solutions for m, n, and p, and I'm going to do this now in a very maths challenge sort of way. So this wouldn't be like a full rigorous mathematical proof if I didn't have the answers in front of me, but we know the answer has to be one of these 5. So let's just go through and see if any of them are possible. So let's see if we can do it with p equals 6, right? So I would need 1 over m plus 1 over n plus 1/6 is 1/2, and okay, so 1/2 minus 1/6, that gives me 2/6. So I'd need these two add together to give 2/6, and then we can see we can easily do this by just taking m and n to both be 6. So I'd get 1/6 plus 1/6 plus 1/6 is equal to 1/2. So I could just have 3 hexagons all meeting together. So A is certainly a possibility here. Okay, let's try and do it with B. So you might not start with the smallest ones, by the way. I mean, I'm going to do this reasonably thoroughly here. So if I tried to take p equals 20, I would need 1 over m plus 1 over n plus 1/20 equals 1/2. Okay, so I'd need 1 over m plus 1 over n is 1/2 minus 1/20. Okay, so that's 10/20 minus 1/20. That's 9/20, and you can see fairly easily here that if you do 1/4 plus 1/5, you get exactly 9/20 here. So B is certainly possible as well. If we try it with C, well, I'd want 1 over m plus 1 over n is equal to 1/2 minus 1 over 42 this time. So that would be 21 over 42 minus 1 over 42, so that would give me 20 over 42, which is 10 over 21. And again, we can see here fairly easily, you've got 7 times 3 is 21, and 7 plus 3 is 10. So 1 over 7 plus 1 over 3 gives us 10 over 21. So I could take m, n, and p to be 3, 7, and 42, and C then works. So certainly we've ruled out the answer to the question being A or B. Now if I try p equals 50, now this time I need 1 over m plus 1 over n is equal to 1/2 minus 1/50. So that's 25/50 minus 1/50, that's 24/50, which is 12 over 25. Now this time we can see that if this is going to work, 1 over m plus 1 over n, to give the simplified fraction having a denominator of 25, basically either m or n is going to have to be a multiple of 25 here. I can't just do like a fifths plus a fifth, that would just give me something in fifths. Now if p is 50, that means the only options would be doing like 1/25 plus something, and or 1/50 plus something. And I'll just leave you to check here that when you do 12/25 minus 1/25 would leave me with 11/25, that's not 1 over something, and 12/25 minus 1/50, that would give you 23/50, that's not 1 over something either. So there aren't going to be any fractions here with whole numbers that make this work. Okay, I'm doing this in a bit of a sort of hacky maths challenge way, but we can see here that D is not possible. And we can also see the same for 100. If you do 1 over m plus 1 over n plus 1 over 100 equals 1/2, so I would need 1 over m plus 1 over n is 1/2 minus 1/100. That would be 49/100. In the same way, I need a factor of 25 in one of these fractions, so it's either got to be 1/25, 1/50, 1/75, or 1/100 for one of these. And I'll just leave you to check that when you do 49 hundredths minus each of these fractions, you don't get something you can write in the form 1 over n, and so we can just see that those cases are all impossible. You might be able to do that last bit in a bit more of an efficient way. And if we thought about this a bit more, we could perhaps come up with a proof that didn't require just using the answers here. But the point of this course here is to help you get ready for the maths challenge, and I wanted to show you how I would do this question if I was thinking about it in a maths challenge way. I'm really, in the maths challenges, trying to get some nice mathematical answers, but I'm just also trying to use the time I've got available as efficiently as possible. So if using the answers can help us get there more quickly, we should definitely do that. And then after the challenge, perhaps we can go away and think about why it's true in some deeper sense. So really well done if you got to that answer, however you got to it, and that brings us to the end of the 2020 Senior Maths Challenge paper.